This is my Precalculus course. Today we're going to prepare for the first test. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. As I've mentioned in my previous courses, there are some subjects where you can study an hour the night before and get a perfect score on the exam. Math doesn't work that way. With math, you need at least 2 or 3 days to study for a test. But it doesn't matter how many times you tell students to study for a test, they're not going to do it. So in order to force you to do at least some studying, we're going to do a practice test right now, version 1. And I'm going to give you a practice test for homework. And these tests are not only going to force you to do at least some studying, they're also going to familiarize you with the format of the test so that you can't say that you were tricked. Now, if you want to get a really good score on the exam in the next class, then you need to study all the problems that we did in the previous classes. These practice tests will hopefully ensure that you at least pass the test, but they won't ensure that you get a really good score. So keep that in mind. And remember, the purpose for taking tests is to prove that you actually know something. Unless you can prove that you can do these problems on your own without any help from anybody, then we haven't really accomplished anything in this course. So that said, let's get started. Again, this is version 1, and we're going to take this practice test. Notice no calculators are allowed. And I want you to attempt these problems on your own before just watching me do them. Now, if you don't remember how to do them, that's okay. But if you attempt the problem on your own and you find out that you don't know how to do it, well, what does that tell you? Well, it tells you you have to study that particular type of problem. So go ahead and attempt problem number 1. And if you can't do it, we'll do it together. Okay, we're back. So this is a polynomial. This expression. This is not a polynomial because of this term here. That's an exponential expression in the sense that the variables are in the exponent, so that doesn't qualify. Here we have 2 terms that disqualify the expression from being a polynomial, because if we change this to an exponent, we have x to the 1/2. We can't have fraction exponents with polynomials, and we can't have negative exponents with polynomials, at least not the variable. And this last expression is well, it qualifies as a polynomial. So if you got that right, excellent. Okay, go ahead and try number 2, and when you come back, we'll do it together. Alright, we're back. So we have -3 x to the 4th, then we're going to add these 2 terms here. So 2x cubed plus x cubed is 3x cubed. And then we're going to add these terms. -5x squared plus -8x squared is -13x squared. And then we have 2. So if you got that right, excellent. Go ahead and try number 3, and when you come back, we'll do it together. Alright, we're back. So you can divide each term by 3x squared. So 27 divided by 3 is 9. And x to the 4th over x squared, that's the that's one of the exponent rules. We just subtract the exponents. 4 minus 2 is 2. 81 divided by 3 is 27. and 3 minus 2 is 1, so we just have x to the first power, which is just x. 30 divided by 3 is 10, and x squared divided by x squared would just be 1. So there we go. If you got that right, excellent. Okay, go ahead and try number 4, and when you come back, we'll do it together. Okay, we're back. So where is this function increasing? Well, it's increasing from here to here. So that's 1, 2, 3, 4, 5, 6, 7. And the y values are also increasing from 3 to positive 7. And the y values are decreasing from 0 to 3. Remember, when the problem asks where the function is increasing, it means where are the y values increasing. When it asks where the function is decreasing, it wants to know where the y values are decreasing. So if you got that right, good. Okay, go ahead and try number 5. When you come back, we'll do it together. Okay, we're back. So we want to know the potential rational zeros using the rational zeros theorem. So P is 2, Q is 3. We want to find the factors, which are 1 and 2, and 1 and 3. So if we take 1 and 2 and divide them by 1, we get 1 and 2. And then if we take 2 and divide by 1 and 3, or excuse me, if we take 1 and 2 and divide them both by 3, we get 1/3 and 2/3. So those are all the potential rational zeros for this function. And so I think that's it for problem number 5. If you got that right, good. Try number 6. When you come back, we'll do it together. Okay, we're back. So notice that the degree of this function is 5. So the maximum number of turning points of the corresponding graph of this function is going to be 5 minus 1, which is 4. So if you got that right, excellent. Go ahead and try number 7. When you come back, we'll do it together. Okay, we're back. So we have to analyze the first term here. If we plug in very large values of x, large positive values of x, then we're going to raise those values to the 5th power and then multiply by a positive number. So what that means is that as x becomes very large, as it becomes a very large positive number, this first term is going to become a very large positive number. So remember, the first term tells you everything about the end behavior of the function. So as x approaches infinity, meaning as x gets really big, the y values also get really big. Now, if you plug in really big negative numbers and raise them to the 5th power, when you raise a negative number to an odd power, in this case 5, then you get another negative number. And if you multiply that negative number by a positive number, 3, then you're going to get a negative number. So as x becomes a very big negative number, this first term will become a very big negative number. And again, the first term, the term with the highest power of x, tells you what the end behavior is going to be. So as x becomes a very large negative number, the y values will become a very large negative number also. So there you go. That's how we describe the end behavior of a function. So if you got that right, excellent. What this means is that if you were to graph the function, as x gets really large, the graph would go up, but as it gets really small, when we plug in really big negative numbers, the graph is going to go down as you go to the left. So it goes up as you go to the right, it goes down as you go to the left. Okay, try number 8, and when you come back, we'll do it together. Alright, we're back. So we can see the zeros just by looking at this this function, because it's in factored form. Plug in 1, you get 0. Plug in -2, you get 0. So we wrote the zeros. We also need to write the multiplicity of each 0. So the multiplicity of this 0 is 6, because that's the exponent of that corresponding factor. And the multiplicity of this 0 is 3. And I guess we can say multiplicity uh, 6 and multiplicity 3. And we want to know whether or not the graph crosses at these zeros or just touches the x-axis. So this is an even multiplicity, which means the graph just touches. It doesn't cross the x-axis. It just touches the x-axis. But here we have an odd multiplicity, so that means that the graph actually crosses the x-axis at that 0. So there you go. And it's probably good to write x is equal to 1 and x is equal to 2 just to be thorough. So again, if you got that one right, excellent. Okay, so go ahead and try number 9. When you come back, we'll do it together. Okay, we're back. So we're going to divide using synthetic division. So we don't really need a lot of room. But we do have to be careful here because, well, we start with 3. Then we go to 4, and then we need a 0 because there's no x cubed term. There's no x to the 3rd power term. Then we have an x squared term, but then we don't have any x term. So we need a 0 because there's no x to the 1st power term. But also, not only is there no x to the 1st power term, but there's no term without an x. So we have to put another 0. So you really have to be careful. And before we even go on, we should probably rewrite this just to make it clear what we're doing here. So we have to order these correctly. That's number 1. And here we should write x minus 2 instead of -2 plus x. That's going to make it a lot easier for us. And so we're dividing by x minus 2, but remember we want to write the 0 here. The 0 is not -2. The 0 is actually +2. It's what you plug in here to make that 0. Okay, so now we're going to use the synthetic division algorithm. We're going to bring down the 3 and then multiply these two numbers and write it there, and then we're going to add these. Then we're going to multiply these two numbers, and then we're going to add these. Then we're going to multiply these two numbers. We're just using the same algorithm over and over again. Then we're going to add these. Then we're going to multiply these two numbers. Then we're going to add these. Then we're going to multiply these two numbers. And then we're going to add these. And we're done. So we divided using synthetic division. So now we can use these numbers to write the quotient. So the power is going to be 1 less than the degree of what we started with. So this is going to be 3x to the 4th power plus 10x cubed plus 20x squared plus 42x plus 84 plus the remainder over the divisor, which is x minus 2. So that's where I got all those numbers. So there you go. If you got that right, excellent. Okay, so go ahead and try number 10, and when you come back, we'll do it together. Okay, we're back. So we can actually factor this pretty easily. What two numbers multiply to 25 and add up to -29? Actually, they're not going to add up to -29, but we just need two numbers that multiply to 25. Now, they both have to be negative, because this number is positive and this number is negative. If we add these up, we get -25, the inner terms. So that doesn't work. So that doesn't really help us. So let's try -25 and -1. And that does help us. So it looks like we have the correct factorization, and by the way, you can FOIL this out to confirm. So the f terms, multiply those, you get 4x to the 4th power. And the outside terms, multiply those, you get -4x squared. Then multiply the inside terms, you get -25x squared. Then multiply the last terms, and you get +25. So that's how you confirm that the factorization is correct. Add these together, you get -29x squared. Okay, so now we have the difference of two squares here and here, so we can continue to factor. So we have 2x minus 5, 2x plus 5. So that factored to that. And then this is going to factor to x plus 1 and x minus 1. So we want to find the zeros of the following function. So the zeros are just whatever x values you can plug in to make the function equal to 0. So we have x is equal to 5/2. That's what you plug in here to make this factor 0. X can be equal to -5/2. X can be equal to -1, or x can be equal to 1. So those are the zeros of that of that function. So if you got that right, excellent. Go ahead and try number 11, and when you come back, we'll do it together. Okay, we're back. So we want the leading coefficient to be -2, and we know 2 is a 0, which means that x minus 2 is a factor. So that is the factor theorem that tells us that. And we want a degree 3 polynomial, so that means there's going to be 3 factors. And we know that 2 plus 3i is a 0. But remember, we have the complex conjugate theorem that tells us that if 2 plus 3i is a 0 of a polynomial, then 2 minus 3i must be a 0 of that same polynomial also. Now that's only if you have real coefficients on your polynomial. But again, we're assuming that we do want real coefficients. It tells us that. So again, if this is a 0, then 2 minus 3i must be a 0 also. Now, why did we write it like this? Well, because if you plug in this here, then it'll make this factor 0, right? Because you have 2 plus 3i minus 2 plus 3i is 0. So that's why we wrote it like that. Again, that's the factor theorem. So now all we have to do is simplify. And I'm going to distribute the negative. You don't have to do it this way, but that's just the way that I prefer to do it. And we have a lot of math to do here. So I'm going to multiply these first. So we're going to multiply x by x, then x by -2, then x by 3i, and we get 3xi. You can write it however you want to. Then we're going to move on to the -2. -2 times x is -2x. -2 times -2 is +4. -2 times 3i is -6i. Then we're going to move on to the -3i. -3i times x is -3xi. And then -3i times -2 is +6i. And then -3i times 3i is +9. Okay, so now we're going to combine the -2x's to -4x. These terms cancel out, and these terms cancel out. So it looks like we're going to be left with 4 plus 9, which is 13. So then we have to keep multiplying. X times x squared is x cubed. X times negative 4x is negative 4x squared. And x times 13 is 13x. Negative 2 times x squared is negative 2x squared. Negative 2 times negative 4x is positive 8x. And negative 2 times 13 is negative 26. So we can simplify. So we have x cubed, and combining these terms, we have negative 6x squared. And combining these terms, we have 21x. And then we have negative 26. So that looks correct. Now we can multiply everything by negative 2. And we have negative 2x cubed plus 12x squared plus 42x. Actually, minus 42x. And then plus plus 52. So that was, or that is the polynomial that we're looking for. So if you got that right, excellent. Okay, on to number 12. It says solve, write the following, or write the solutions graphically and in interval notation. So we have a bunch of inequalities here. So what we can do, notice we have a common denominator among all these fractions, so that's going to be helpful. We want to put everything on one side. Remember, that's the first thing that we have to do with nonlinear inequalities. So I'm going to subtract x over x cubed minus 64 from both sides of the equation. You don't have to show that, but I'm just demonstrating what we're doing. And notice that these we can actually combine. They have a common denominator, so 2x minus x would just be x. So we have 3 over x cubed minus 64 plus x over x cubed minus 64. And we can continue to combine the fractions because they have common denominators, so why not combine them? So now we're ready to go, but we need to do a sign chart. We need to write a sign chart. Actually, before we do that, let's continue. I forgot to do one step. We need to factor. Now, this is the difference of two cubes. And remember, we have a formula for the difference of two cubes. Here's the formula. So we're going to have x minus 8. Well, actually, that should be a 4. Sorry, that should be a 4 there. Plus 4x plus 4x plus 4 squared. So let's double check that. And it might be good to write 64 as 4 cubed, so then you can see it's the difference of 2 cubes in the denominator. Okay, so if you try to factor this, you'll notice that it's not really easily factored. In order to determine that, we want to find the discriminant of that quadratic expression, which is b squared minus 4ac. And b is going to be this number here, and a is going to be this number, and c is going to be this number. So we have 4 squared minus 4 times a times c. So we have 16 minus 64, which is negative 48. So the discriminant is negative. What that means is we can't really factor this very easily, but also our factors would have imaginary numbers in them, so we don't have to continue to factor. So now we're ready to draw a sign chart, and the numbers that we're interested in are the values that make the denominator 0 or the numerator 0. So 4 makes the denominator 0, and negative 3 makes the numerator 0, because this would be an x-intercept and this would be an asymptote. And again, we don't have to worry about this factor here. So now let's do a sign chart. Let's test the middle region here. If we plug in 0, we want to know the sign of this expression. So if you plug in 0, you can do the math real quickly in your head, and you find that it's a negative number. We don't really care about the actual value of the expression. We just want to know whether it's positive or negative. So that would be a negative. And over here, let's test 5. Plug in 5, and you see we get a positive number. And if we plug in negative 4, that's a little harder to see, but let's try. Negative 4 squared is 16, minus 16 is 0, plus 16. So this term, or this factor, would be positive. And then plug in negative 4 here, and that factor would be negative. So let's keep track of this. That would be positive times a negative. And then in the numerator, we plug in negative 4, and we get a negative. So do the math, and we see that we have a positive number. So now we have our sign chart. And so now let's draw the graphical solution. Notice it says it wants this expression to be greater than or equal to 0. So we're going to have to, well, for x plus 3, if we plug in negative 3, we get 0. So that's okay to have a closed dot there. And we want it, again, we want this expression to be greater than 0, so we're going to shade in this region where it's positive. That's where the expression is greater than 0. And over here we have an asymptote, which means that the expression really is not defined there, so we're going to need an open dot there. but we can color in this area here because we again want the expression to be positive, meaning greater than 0. So that is the graphical solution. Okay, so now let's draw the solution in interval notation. So we have negative infinity to negative 3 with a bracket, then union symbol, and then a parenthesis, and 4 comma infinity. So that is the answer in interval notation. So we got that right. Excellent. Okay, so go ahead and try number 13, and when you come back we'll do it together. Okay, we're back. So we start by putting everything on one side of the inequality. And then we're going to factor out x squared because it just turns out that we can factor by grouping. You always want to factor by grouping if you can when you have a degree 3 or greater polynomial. So we factored out x squared from these terms, and we factored out negative 4 from these terms. And now notice we can factor out x plus 5 from this term and this term because they both have that same common factor. And you're left with x squared minus 4. Well, now we have the difference of two squares, so you can continue to factor. X squared minus 4 becomes x plus 2 times x minus 2. That's the difference of two squares. And so now we're going to do a sign chart. So we have 2 and negative 2 and negative 5. Doesn't really matter if the spacing is correct. That's not really what's important. So let's test 0. That's always the easiest value. So let's plug in 0 to this expression, and we get a negative number. So this region is going to be negative. Let's plug in 4, or let's plug in 3 to test that region, and we get a positive number. And we know the multiplicity of each one of these is 1, so we know that the signs are going to change. Let's plug in negative 3, and we get a positive number. Again, notice that the signs are changing at each critical number because, again, the multiplicity is 1. It's 1 for each one of these factors, so that's an odd multiplicity. Now let's try plugging in negative 6, and we get a negative number, as you would expect. So now let's draw the graphical solution. So it says greater than, but it doesn't say equal to, so these are all going to be open dots. And it wants this expression to be greater than 0. So what are the x values that make it greater than 0? Well, that's this region here, and this region here. So that is the graphical solution. Now let's draw the solution in interval notation. So there you go. If you got that right, excellent. So go ahead and try number 14, and when you come back we'll do it together. Okay, we're back. So remember, the first step is to put everything on one side of the inequality. Second step is to factor. And so then we can do a sign chart. And let's test the regions. So we're going to plug in 0 and we get a positive number. Plug in 3 and we also get a positive number. So now let's draw the graphical solution. And we want this to be a closed dot because it says less than or equal to. And we want this expression to be less than or equal to, but it's not less than because the expression is positive in those regions. So the only x value that satisfies this inequality is when x is actually equal to 2, because then it makes this expression 0. So this is the graphical solution. It's just one dot. And it doesn't really make sense to use interval notation to write the solution because we don't have an interval, but if we had to write it in interval notation, we could just write 2, 2 with brackets. So if you got that right, excellent. Okay, so go ahead and try this next problem. Solve the inequality, and when you come back, we'll do it together. Alright, we're back. So the first thing we want to do is put everything on one side of the equation. So I'm going to subtract 2 from both sides of the equation. And then I'm going to rewrite 2 as 2 over 1. And so then I'm going to multiply both sides of that fraction by x plus 3 so that we can get a common denominator. And we want to combine those expressions. Okay, and now we're going to subtract the fractions because we have a common denominator. So x minus 2x is negative x, and 1 minus 6 is negative 5. So we can take that negative and put it out in front if you want. That might make it a little easier to analyze this expression. So now we have put everything on one side and combined everything to one expression. And now we're going to use a sign chart to help us solve the inequality. So our numbers of interest are negative 3 and negative 5. Negative 5 makes the numerator 0. Negative 3 makes the denominator 0. So let's test 0 over here. If we plug in 0, we make this expression negative. Negative 5/3 to be exact. If we plug in negative 4, then we get a positive number Again, you can do the math on that if you want. We're just plugging in -4 for x and then figuring out if this expression is positive or negative. So now let's plug in -6. And if we do that, we get a negative. So that is our sign chart. Now we're ready to draw the graphical solution. -3 has to be an open dot because the function is not defined when x is -3. Now this expression is defined when x is equal to -5. When x is equal to -5, we have 0. But the problem is we want to know all of the values of x that make this expression greater than 0. -5 makes the expression equal to 0, so we're going to have another open circle. And again, the expression is positive when x is between -5 and 3, or -5 and -3. So we're going to color in that part there. So that is the graphical solution, and the solution in interval notation is the following. So if you got that right, good. Okay, so now we're going to go to a graphing problem. Try number 16. When you come back, we'll do it together. Okay, we're back. So we want to find the horizontal asymptote equation. You could just divide these two coefficients and then you'd have your horizontal asymptote. Y is equal to 1. Whenever the degree in the numerator is equal to the degree in the denominator, you can just divide the coefficients of the leading term. 1 divided by 1 is 1. But if you want to know exactly why that works, then we're going to use long division. So we're going to divide the numerator by the denominator. So x squared times what is equal to x squared? Well, that's just going to be 1. 1 times x squared is x squared. 1 times 2x is 2x. 1 times -8 is -8. Then we're going to subtract. X squared minus x squared is 0. -4x minus 2x is -6x. And 3 minus -8 is 11. So now, if we rewrite the rational function, it would look like this. 1 plus -6x plus 11 over x squared plus 2x minus 8. So it's very important to understand that this green expression, sorry, my computer's going slow, this green expression and this green expression, they're equal. Whoops, that should be -8. They're equal expressions. They mean the exact same thing pretty much. But we just changed the form. And the reason we did that is because now we can see that as x gets really big, because you have a x squared term in the denominator is just going to get bigger and bigger and bigger. And it's going to outrun the numerator. So this entire fraction is just going to approach 0 as x gets really big. So what that means is that the graph is going to approach 1. Y equals 1. So there's going to be an asymptote at y equals 1. That's the logic behind that. So this tells us that the horizontal asymptote is going to be y is equal to 1. So let me move this over. Okay, so now the vertical asymptote equations, well, how do we figure that out? Well, we have to factor. In fact, it's going to be beneficial for us to factor the numerator and the denominator, if we can factor easily. So here we have x and x, and minus 3 and minus 1. And here we have plus 4 and minus 2. So the vertical asymptotes are the numbers that make the denominator 0. So the equations are x is equal to negative 4 and x is equal to 2. So those are the asymptote equations, the vertical asymptote equations. And the y-intercept, well, we just plug in 0 for x, and we get negative 3/8. So the y-intercept is 0, comma, negative 3/8. And to find the x-intercept, well, we can see what the x-intercepts are going to be. It's just whatever makes the expression 0, and the numerator is going to tell us that. But we can bring this down just to demonstrate. You don't have to. But we want to figure out what makes f of x equal to 0. Trying to figure out what makes that equal to 0, and the answer is x is equal to 3 or x is equal to 1. So what this means is that we have the points 3, 0 and 1, 0 on the graph. Okay, so now we're going to go ahead and graph the function. So again, we have a horizontal asymptote at y is equal to 1, and vertical asymptotes at negative 4, and positive 2. And we have a y-intercept at 0, negative 3/8. Should be about there. We have x-intercepts at 3, 0 and 1, 0. Okay. Now we need to do a sign chart. So let's write our critical numbers. We have 3, 0 and 2 is an asymptote, and we have 1 is a x-intercept, and we have negative 4. Okay, so those are all the critical numbers. So let's test the regions. Let's test 0 first. So we can plug in 0 up here, and we get positive divided by a negative, so that would be negative, that region. Now let's test 4. We plug in 4, we get a positive. This expression is going to be positive. And if we plug in negative 5, we get a positive divided by a positive, which is positive. And if we plug in 1.5, again, we don't care about the actual value, we just want to know if it's positive or negative. Plug in 1.5, then we get a negative divided by a negative, which is a positive. And then if you plug in 2.5, we'll get a negative divided by a positive, which is a negative. Again, you can do this really quickly just by looking at these factors. So now we're ready to draw our graph. So we know that this region over here is going to be above the x-axis. So it looks like it's going to be something like this. We have a negative number here, so we know this region is going to be below the x-axis, so it looks like it's going to do something like this. And then we have a region, well, it should be positive, so it looks like the graph is going to do something like that. And then we have a negative region from 2 to 3, so our graph is going to be coming up like this, and then positive, and it's going to follow that asymptote. So there you go. So that is how you graph one of those rational functions, not exactly something that is simple. That's why we have to use all kinds of sophisticated math techniques to graph that. So if you got that right, excellent. Okay, now we're going to graph another rational function. And the first thing we can do is factor we have the difference of two squares in the denominator. And notice that these just cancel out. And we're left with a different function that I'll call g of x. It's not the same thing because it's missing a whole. Because those factors canceled out, we know we have a whole at x is equal to 3. Okay, and vertical asymptotes, well, this is a vertical asymptote because it didn't cancel out, so x is equal to -3 is a vertical asymptote. Horizontal asymptotes, well, this is a proper fraction because the degree of the numerator is smaller than the degree of the denominator. The degree of the numerator is 1, the degree of the denominator is 2. So that means there's always a horizontal asymptote at y is equal to 0. To find the y-intercept, we let x equal 0. And we end up with 1/3. So the y-intercept is 0, 1/3. And to find the x-intercept, we let f of x be equal to 0. And f of x is x minus 3. Well, we can just say x minus 3 over x squared minus 9. But notice that factor canceled out, so we're left with this expression. There is no value that would make the expression equal to 0. There's a value that would make it undefined, that would be 3, that's a whole. But there's no value of x that would make the expression equal to 0. Okay, so now let's use our vertical asymptote to write a sign chart. The vertical asymptote is it's going to be the only thing that really helps us with the sign chart. We don't have an x-intercept. Remember, the x-intercepts and the vertical asymptotes, they really help us to determine our sign chart. So let's try plugging in 0 into this expression up here. And we'll get a positive number. Now let's try plugging in -4. And we get a negative number. So let's draw our vertical asymptote. So here's our vertical asymptote. And let's draw our horizontal asymptote. And let's draw our y-intercept, which is 0, 1/3. And I think we're ready to go. So we know the graph is positive in this region here. So that means it has to be above the x-axis. And we know it's negative in this region here, so it has to be below the x-axis. Now we do have a hole at x is equal to 3. So we have to count out 1, 2, 3 and make sure we put a hole there. So I'm going to erase that and draw a hole. So there you go. If you got that right, excellent. Go ahead and try number 18. When you come back, we'll do it together. All right, we're back. So it would be helpful for us to factor this. And the vertical asymptotes are x is equal to 4 and x is equal to -3. And this is a proper fraction because the degree in the numerator is smaller than the degree in the denominator, so that means we're going to have a horizontal asymptote at y is equal to 0. To find the y-intercept, we simply let x equal 0, and we get -1/12. So we know 0 and -1/12 is on the graph. And then to find the x-intercept, we let f of x equal 0. And the only value that would allow that to happen can be found by looking at the numerator. What makes the numerator 0? Well, it's x is equal to -1. So -1 comma 0 is the x-intercept. So we need to pay attention to the x-intercepts, or the one x-intercept and the two vertical asymptotes. So we have 4, we have -1, and -3. So that's test 0. Let's plug in 0 up here, and we get a negative number. We could have seen that just by looking at that number there. Let's plug in 5, and we get a positive number. Plug in -2, and we have a negative divided by a negative times a negative. Actually, a negative times a positive, so that would be a positive number. Again, we're determining the sign of this expression. So now let's plug in -4. So we have a negative divided by a negative times a negative, which will give us a negative number. Okay, so I think we have everything that we need. Let's graph our vertical asymptotes at x equals 4. And x equals negative 3. And we have a horizontal asymptote at y equals 0. And we have an x-intercept at negative 1, 0. And we have a y-intercept at 0, negative 1, 12. And we don't have any holes because none of these factors canceled out. So now, using our sign chart, we can draw this graph. So over here we should have a negative values, so our graph is just going to look like this. In this region we should have positive values, so it looks like our graph is going to look like this. Then in this region it should be negative. Below the x-axis means negative, and in this region we should have positive y values. So there you go. And again, there's no hole in that problem. So if you got that right, excellent. Okay, now we need to divide. So we're going to use the long division algorithm. We cannot use synthetic division because this divisor is not the right type of divisor. We need x minus some constant or x plus some constant. If we don't have these types of divisors, we can't use synthetic division. Okay, so x squared times what is equal to 2x to the 6th power? So that's just going to be 2x to the 4th power. So then we're going to multiply 2x to the 4th power by that whole divisor. Two x to the 4th times x squared is 2x to the 6th. 2x to the 4th times x is 2x to the 5th. And 2x to the 4th times negative 2 is negative 4x to the 4th. So then we're going to subtract. These cancel out. 0 minus 2x to the 5th is negative 2x to the 5th. 0 minus negative 4x to the 4th is positive 4x to the 4th. And now we're ready to start a new algorithm. Or start the not a new algorithm, but to start the next cycle of the algorithm. So now we're going to ask x squared times what is equal to negative 2x to the 5th. That's going to be negative 2x to the 3rd. So now we multiply negative 2x to the 3rd times this divisor, and we get negative 2x to the 5th minus 2x to the 4th plus 4x cubed, and then we're going to subtract, and we get 6x to the 4th minus 4x cubed. These cancel out, of course. And now we're going to start the third cycle. So now we're going to ask what number times x squared is equal to 6x to the 4th and that's going to be 6x squared. 6x squared times this whole divisor is going to be 6x to the fourth plus 6x cubed minus 12x squared. Then we're going to subtract. These cancel out, as they should, and we get negative 10x cubed plus 12x squared. 0 minus negative 12x squared is 12x squared. So I know that this is a long process, but you have to do it. So now we'll start the cycle over again. X squared times what is equal to negative 10x cubed. Negative 10x, it looks like. So now we're going to multiply this by this divisor, so we have negative 10x cubed minus 10x squared plus 20x. Subtract, and these cancel out, and you get 22x squared minus 20x. And now we're going to keep going because our degree here is equal to the degree here, so we need to do one more step. So now we're going to ask what number times x squared is equal to 22x squared. So that's going to be 22. So now we're going to multiply 22 by that divisor, and we get 22x squared plus 22x minus 44. And then we'll subtract, so we get negative 42x plus 44. So the final answer would be 2x to the fourth minus 2x cubed plus 6x squared minus 10x plus 22. I got that number from up here, plus negative 42x plus 44 over the divisor, the original divisor, x squared plus x minus 2. So there you go. I probably won't give you a problem on the test. It is quite that difficult, because that was kind of tedious. Okay, so if you got that right, excellent. Go ahead and try number 20, and when you come back, we'll do it together. Alright, we're back. Find the roots of the polynomial function below. So this is a pretty complicated function, so we're going to have to use the rational roots theorem, or the rational zeros theorem, whatever you want to call it. So P is 30 and Q is 1, and the factors of 30 are 1, 2, 3, 5, 6, 10, 15, and 30, and the factors of 1, of course, are just 1. And if we divide all these numbers by 1, then we just get those numbers, and we don't have to write every single one. So I'm just going to write dot dot dot, because we may not need all of those. So now we're going to test these possible or potential rational roots. We're going to test them by plugging them into the function and seeing if the function is equal to 0. So let's try x is equal to 1 first. I got that from here. So we don't want to show all the work, because that would take forever. So we're just going to do it in our head. So plug in 1, we get 1 minus 3 is negative 2, minus 15 is negative 17, plus 19 is 2, plus 30 is 32. That did not work. That's okay. Now we're going to plug in -1. Let's see if that works. -1 to the 4th power is +1 minus, well, it's too hard to recite all this math, so we'll just do it in our heads. So 1 plus 3 is 4, minus 15 is -11, minus 19 is -30, plus 30 is 0, so that actually worked. So I'll give a check on that. So we know that -1 is a 0, so by the factor theorem that means that x plus 1 is a factor. So if we divide the polynomial by x plus 1, and we can use synthetic division for this because we're dividing by the correct divisor, correct form, then we can figure out the reduced form of the polynomial. It'll help us to find the other zeros. So I got all these coefficients from up here, and remember the 0 itself goes there. So let's get started. We're going to bring down the 1, then multiply these numbers and we get -1. Add these numbers, we get -4. Multiply these numbers, we get +4. Add these numbers, we get -11. Multiply these numbers, we get +11. Add these numbers, we get +30. Multiply these numbers and we get -30. Add these and we get 0. So now we have the reduced form of the polynomial. We always start with a degree that's 1 less than what we started with. Okay. So now we can continue to test the reduced polynomial. So I tried -1, but remember you can try -1 again to make sure it doesn't work twice. So let's plug in -1. We get -1 minus 4 is -5, plus 11 is 6, plus 30 is 36. So that didn't work. So it didn't work. Let's try plugging in 2. We plug in 2, we get 8 minus 16 is -8. Minus 22 is -30, plus 30 is 0, so that worked. So now we're going to perform our synthetic division again, but now on the reduced form, or the reduced polynomial. And maybe we should space this out a little bit. And we're going to divide by 2 this time, or x minus 2 to be exact. So I'm going to bring down the number, multiply these two numbers, write it here, add these two numbers, multiply these two numbers, add these two numbers, multiply these two numbers, and then add these two numbers. And we should get 0. If we don't get 0, we did something wrong. So now we have a degree 3, and the reduced polynomial is going to have a degree 2. Its degree is going to be 2. So notice up here it says write the function in factored form. So I'm going to go ahead and do that, because we're ready to do that after we factor this. But what we've figured out so far is that we can factor this polynomial up here so that we have x plus 1 times x minus 2 times x squared minus 2x minus 15. So this factor up here gave us, or that 0 gave us that factor, and this 0 gave us this factor, and our reduced form here got us to that point. But we have to keep going so we can continue to factor. I believe that expression will be factorable, at least I hope it will. So I think we can factor that orange expression to x minus 5 times x plus 3. So that is the factored form, and we're asked to find the roots. So now that we have it in factored form, we can easily see the roots. -1, 2, 5, and -3. So here is one solution. And here's the second solution. So if you got that right, excellent. Okay, so go ahead and try number 21. When you come back, we'll do it together. Okay, we're back. So we're going to have to use the long division algorithm. Synthetic division doesn't work because we don't have the right divisor. I know it's tedious to have to write all this out, but we have to do it. So let's start our first cycle. So x squared times what is equal to x to the 5th? Of course, that's x cubed. Now we're going to multiply x cubed by the divisor, and we get x to the 5th plus x plus 4x to the 4th plus 4x cubed. Now we're going to subtract, and these cancel out obviously. Negative 4x to the 4th minus 4x to the 4th is negative 8x to the 4th. And subtract these, and we get negative 13x cubed. And then you can bring down the other terms. And now we're going to start another cycle. So x squared times what is equal to negative 8x to the 4th power. That's going to be negative 8x squared. Now we're going to multiply negative 8x squared by the divisor. We get negative 8x to the 4th minus 32x cubed minus 32x squared, and if we subtract, these cancel out, and negative 13 minus negative 32 is looks like that's going to be 19x cubed, and 32 minus negative 32 is positive 64. And we can bring down the rest of the terms. And now we start the cycle over again. X squared times what is equal to 19x cubed. And that's going to be 19x. Now we're going to multiply 19x times the divisor. We get 19x cubed. And 19 times 4 is 76, so we get 76x squared. Then 19 times 4 again is 76x, and subtract, and we get negative 12x squared, and negative 48x, and negative 48. So now we're ready to start the cycle over again. We have one more cycle because we have equal degrees here. So one more cycle. So x squared times what is equal to negative 12x squared. That's going to be negative 12. So multiply negative 12 by the divisor. And we get negative 12x squared minus 48x minus 48, and then our divisor is our remainder is 0. So this particular problem didn't really have a remainder, so our answer is this expression up here, x cubed minus 8x squared plus 19x minus 12. So if you got that right, excellent.
Go ahead and try number 22. When you come back, we'll do it together. Okay, we're back. So we're going to use the irrational zeros theorem. P is 18, Q is 1. And so the factors of 18 are 1, 2, 3, 6, 9, and 18, and the factors of 1 are 1. So P over Q is plus or minus 1, plus or minus 2, so on and so forth. So we're just dividing these numbers by 1. And so now let's test. Our first value is test 1. So we have 1 minus 2 is negative 1, plus 4 is 3, minus 6 is negative 3, minus 15 is negative 18, plus 36 is 18, minus 18 is 0. So that works. So we can use synthetic division and write the coefficients. And we're dividing by x minus 1. Let's double check to make sure we wrote that correctly. It looks correct. And now we're ready to perform the algorithm. And our remainder is 0, so it should be 0. That tells us we did it correctly. So now we can write the reduced polynomial. So that's where we got all those coefficients. And now let's try x equals 1 again in the reduced polynomial. So 1 minus 1 is 0, plus 3 minus 3 is 0, negative 18 plus 18 is 0. So it looks like 1 works again. So we can divide that polynomial by x minus 1 again. So let's perform the algorithm. And our remainder is 0, so we should have 0 for the remainder. Now our reduced polynomial will have a degree that's 1 less than the degree of the previous polynomial. Notice the 0 is the x cubed term, and this is the x term. So fortunately, I think we can factor this without using the rational zeros theorem. But let's write what we have so far. So we know that f of x is equal to x minus 1 times x minus 1 times x to the fourth plus 3x squared minus 18. And so now we just have to factor. It doesn't say to write the factored form, so we don't really need to write the factored form. We're just doing this so you can see how this process is working. So now we can factor this expression here. And that's going to be something that looks like a quadratic. So we have positive 6 and negative 3 multiplied to negative 18, and they add up to 3. So these factors here give us more zeros, and we know that 1 is a 0 because if we plug it in here we get 0. We need to figure out the numbers that we can plug in here to make those 0. So we can write equations if you need to. So I'm going to write those up here. So we can set x squared minus 3 equal to 0 and then solve. And we can set x squared plus 6 equal to 0 and solve. So if we solve in this equation, we get plus or minus root 3. And if we solve in this equation, we get plus or minus I root 6. So we have irrational zeros and we have imaginary zeros. So now let's write the final answer. So our zeros are 1, root 3, negative root 3, I root 6, and negative I root 6. So if you got that right, excellent. Okay, so go ahead and try number 23. When you come back, we'll do it together. Okay, we're back. So it looks like we're going to use the rational roots or rational zeros theorem. So P is 100, Q is 5. And the factors of 100 are 1, 2, 4, 5, 10, 20, 25, and we probably don't need all these factors, but 50 and 100. And then the factors of 5 are 1 and 5. So, now let's find P over Q. We're going to divide all these numbers by 1. We don't have to write all of them, of course. So I'm just going to write the first 4 numbers, actually technically the first 8 numbers because it's plus or minus. So now let's try x is equal to 1. So if we plug in 1, we get 5 plus 5 is 10, minus 80 is negative 70, plus 100, so that doesn't work. So now let's try plugging in negative 1. Then we get negative 5 plus 5 is 0, plus 80, plus 100, so that doesn't work. We want the polynomial to be equal to 0. Now let's try positive 2. 40 plus 20 is 60, minus 160 is negative 100, plus 100 is 0. So it looks like 2 is going to work. Now we can divide that polynomial using synthetic division. And we're dividing by x minus 2. And our remainder is 0, as it should be. So the reduced polynomial is 5x squared plus 15x minus 50. And that's where we got those coefficients. Remember, our degree is 1 less than what we started with. So we don't have to write the factored form of the function, but it's probably best if we do. So we have x minus 2 times 5x squared plus 15x minus 50. And I also noticed that we can factor out a 5 to make things easier for us. It'll make it a little easier to factor this expression. So the question is, can we factor this? And I think we can. Well, technically we can factor any quadratic, but can we factor it easily? Yes, because we know two numbers that multiply to negative 10 and add up to 3. That would be 5 and negative 2. So now we have our zeros, and zeros are the same thing as x-intercepts, at least if they're real. If they're real zeros, they're x-intercepts. So we need to identify the x-intercepts. So we have 2, negative 5, and actually 2 appears twice. So we could rewrite this as x minus 2 squared times x plus 5. So our zeros are 2 and negative 5. And the multiplicity, which is the exponents here, that tells us if the graph of the function crosses the x-axis or just touches. So we have an even multiplicity. 2 is even. So that means that at this x-intercept, the graph touches the x-axis, but it doesn't cross. Now the multiplicity of this 0 is 1. That's an odd number. So that means that the graph of the function crosses the x-axis. So that is the answer, if you got that right. Good. Okay, go ahead and try number 24. When you come back, we'll do it together. Okay, we're back. So it's probably going to be useful for us to factor so what two numbers multiply to -10, they're not necessarily going to add up to -1 because the 2 here complicates things. So we'll try -5. Actually, I'll put the -5 over here and +2, and that works. If you perform FOIL on this, you'll get back to this number, this expression here. So notice that we have a factor that actually cancels out. So that means there's going to be a hole on the graph. So x is equal to 5/2. That's the x value where a hole will occur. But there's another hole because if we factor x to the 4th to x times x times x times x, we can see that one of these x's is going to cancel out. So there's another hole at x equals 0. Now, x equals -2, that's going to be the equation of a vertical asymptote because this purple factor does not cancel out. So now, let's see if we have a y-intercept. So if you let x equal 0, what do we have? Well, we have a hole at 0, so that cannot be a y-intercept because that means that there's the function is not defined when x is 0, so there's a hole, so that's not considered a y-intercept. And is there an x-intercept? So if we let y equal 0, if we let f of x equal 0, can we solve for x? So if f of x is 0, then we need the numerator to be 0 to make that happen. But the only way to make the numerator 0 is to make one of these x's 0, one of these orange x's. But the problem is if one of those x's is 0, then you're going to just end up with the y value of the hole, so there's no x-intercept. So now let's find the curve of the asymptote. So we want to take the original expression, the numerator, and divide by the denominator. And we're going to ask 2x cubed times what is equal to 2x to the 5th power. That's going to be x squared. Then we're going to multiply, and we get 2x to the 5th minus x to the 4th minus 10x cubed and so let's subtract. These cancel out. -5 minus -1 is -4, and 0 minus -10 is +10. And so now we're going to ask 2x cubed times what is equal to -4x to the 4th. And that's going to be -2x. So now we're going to multiply -2x by this divisor. then we're going to subtract. So these cancel out, and we're left with 8x cubed minus 20x squared. And we're almost done because the degree is equal to the degree of the divisor. The degree of the remainder is equal to the degree of the divisor. But we need to continue until the degree is less than. The degree of the remainder is less than the degree of the divisor. So now we're going to ask 2x cubed times what is equal to 8x cubed. And that would just be 4. So now we're going to multiply 4 by the divisor. 4 times 2x cubed is 8x cubed. And negative 4x squared. And negative 40x. So then we're going to subtract, and we get negative 16x squared plus 40x. And so now we're ready to write the resulting expression. So we're rewriting the function in a different form. So we have x squared minus 2x plus 4 plus the remainder over the divisor. So plus negative 16x squared plus 40x over 2x cubed minus x squared minus 10x. So this is just a different way to write this function. We took an improper fraction and made it proper. Now, because the degree of this denominator is greater than the degree of the numerator, that means that as x gets really big, or if x gets if it's a really big positive number or a really big negative number, this fraction is going to approach 0, which means that the graph, as x gets really big, the graph is going to get closer and closer to whatever this curve is. So that is the answer. So the asymptote curve is x squared minus 2x plus 4. So if you got that one right, good. Alright, go ahead and try the last problem here, number 25. When you come back, we'll do it together. Alright, we're back, so we're going to use the rational zeros theorem. So P is 46, Q is 9. So we have 1, 23, and 46, and we have 1, 3, and 9. I think I forgot to write 2. 2 is also a factor. Okay, so let's divide all these numbers by 1. So we have plus or minus 1, plus or minus 2, plus or minus 23, plus or minus 46, so on and so forth. Then we can divide all these numbers by 3. And then we get plus or minus 1/3, plus or minus 2/3, but we don't have to write all of those. Okay, so now let's test x is equal to 1. So if you plug in 1 up here, you get 9 minus 57 is negative 48 plus 131. That would be 83, and then minus 129 is negative 46, and then plus 46 is 0, so 1 works. So now let's divide the polynomial by x minus 1.
And I'm going to bring the 9 down, multiply these two numbers, add these two numbers, multiply these two numbers, add these two numbers, multiply these two numbers, add those two numbers, multiply these two numbers, add these two numbers, and our remainder should be 0. So now our reduced polynomial is 9x cubed minus 48x squared plus 83x minus 46. So the degree of the reduced polynomial is always 1 less than what we started with. So now we want to try x is equal to 1 again. So let's plug in 1 to the reduced polynomial. 9 minus 48 is negative 39 plus 83 is 44 minus 46 is negative 2. So that didn't work. So let's try x is equal to negative 1. So negative 9 minus 48 is negative 57 minus 83, and obviously that doesn't work. So let's try x is equal to 2. Plug in 2, we get 72 minus 48 times 4 plus 2 times 83 and minus 46, we get 0. So looks like that worked. So we're going to perform synthetic division. We're going to divide the polynomial by x minus 2. Drop the 9, multiply the 2 and the 9, we get 18. Add these up, we get negative 30. Multiply these two numbers, we get negative 60. Add these up, we get 23. Multiply these two numbers, we get 46. And our remainder should be 0 if we did it correctly. If it's not 0, then we did something wrong. So now we have 9x squared minus 30x plus 23. So we need to know if we can factor this. Before we do anything, let's review what we've done here. So we've taken the function, and the function is not named f of x, but we can just call it f of x. We've taken the function and we've factored it to x minus 1 times x minus 2 times 9x squared minus 30x plus 23. So we have two of the solutions. We have 2 and 1 are solutions to this equation because they make the polynomial 0. But we need to know if we have any more solutions. So that means we have to factor this last expression, this orange expression. So in order to figure out if we can factor that, I mean, it's not exactly obvious. We can try, but without wasting any time, let's use the discriminant. So I'm going to copy all this and put it up here. And we're going to use the discriminant to figure out if we can actually factor that, if there's going to be real solutions or one solution, or irrational solutions or irrational or imaginary, so on and so forth. So we have b squared minus 4 times 9 times 23. So that is 900 minus 828. So it looks like that's going to be 72. So it looks like we do have real solutions, but they're not going to. This expression is not going to be easily factored. So we do have to use the quadratic formula in order to figure out what those solutions are going to be. But most of the work has already been done for us because we've already found the discriminant. We know that that inside part there is 72. So you can calculate the expression again if you want, but it's not really necessary. We already know the inside part is 72. Whoops, that should be negative 30. Or a double negative. And 2 times 9 in the denominator. So we have positive 30 plus, now this is 36 times 2, so the 36 comes out as a 6. That should be plus or minus. And 18 in the denominator, and then if we simplify, divide everything by 6, and we get 5 plus or minus root 2 over 3. So we could write this in factored form, but we don't really need to. We can see what the zeros are, so if we plug in 5 plus root 2 over 3 into this expression, we get 0. So that is a solution to the equation. If we plug in 5 minus root 2 over 3 into this factor, then we get 0 again. So that's a solution. And of course, if we plug in 2 or 1, we get 0. So those are the solutions. So x can be equal to 1, or x can be equal to 2. Or x can be equal to 5 plus root 2 over 3, or x can be equal to 5 minus root 2 over 3. So if you got those answers, excellent. Okay, so that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2 and number 3 and number 4, number 5, number 6, number 7, and number 8, and number 9. But don't go before you get your homework. Remember, the homework is a practice test. All these tests must be done completely and correctly. So here's screenshot number 1 of the practice test, version 2, for your homework. And screenshot 2. And screenshot 3. 4. 5, 6, 7, and 8. But don't go before you get the answers. Remember, it's not enough just to attempt the practice test. You must do it correctly, so you must check all your work. So here's the answers. So get that practice test done completely, correctly, neatly, and keep it in order in your binder. And I'll look forward to seeing you in the next class where we take test number 1.